Hi everybody, Mr. Lee here. In this video, we're going to go over electric potential. All right, so electric potential comes under the form of many different names. So in front of you are a couple of synonyms that we might use for electric potential. Okay, it could be called electric potential, E-potential, voltage, potential difference, potential, or simply difference. But it's important to know that all of this means the same thing. Now, the variable for electric potential is the capital V, and so are the units, capital V, and that stands for voltage. Now, you might have heard of the term voltage before when we're dealing with electricity, and it's really close to the same thing, all right? Now, the units for voltage is joules per coulomb, and that's actually going to come in handy when we are trying to understand exactly what electric potential means. Joules, of course, being the unit for energy, and coulomb being the unit for charge. So voltage is how much energy you have per unit of charge. Now, to understand what voltage means, we have to actually go back to something that we're a little bit more familiar with, which is the gravitational field. And the reason why I want to do this is because a lot of people misunderstand what voltage represents, right? A lot of people believe that voltage represents power, but that's not necessarily the case. So let's begin. All right. To begin, what I want to do is I want to split my screen into two. All right, on the left, we will talk all about voltage, and on the right, we'll talk all about the gravitational field. All right. So with this, so you know, voltage and gravitational field are not the same, but I'm using the gravitational field as a way to explain exactly what voltage means to us. Okay, using a little bit of analogy. So let's create the Earth here. All right, so I'm going to create some grass. Okay, so that's my floor. Let's create the sky up here. All right, so all right, we have the sky up there. So let's say we have a apple. Okay, we have an apple and it's on the floor. Now, if we were to raise up that apple, let's say to a new height up there, what we did is we changed the height of the apple. Well, of course, okay, this right here we can represent as delta H, or a change in height. Now, in this scenario, let's actually break down the physics behind exactly what we did. So the first thing that we should come across is drawing the field itself. Now, understanding voltage means that you need to have a clear understanding of exactly what is represented, especially when it comes with the field. Okay, so if you have an apple and the apple is under the influence of the gravitational field, and we raise it up to a height like we did here, and we were to release the apple is going to come straight down. It's going to come crashing down. Now, if I were to ask you, why does the apple do this? The explanation is pretty clear, right? We can all say that the force of gravity pulls the apple down. So let's actually draw the force of gravity vector there, okay? F of g, which is equal to mg, right? The mass of the apple times the acceleration due to gravity. G pulls, remember a push or pull is a force, pulls the apple down, okay? And we know that it goes down because the gravitational field right here, okay, shows us that all objects will go towards the downward direction under the influence of gravity. Okay, now what about this delta H, right? What about this height? How does the height come into play in all this? Well, if I were to measure height, right? If this is the gravitational field, I'm gonna do height, and let's do blue. If I were to try to draw in the height, I can say this is, let's say, 1 meter. This right here is 2 meters. Okay, this right here is 3 meters, and let's say we raise the apple up to a height of 4 meters. That's pretty tall. All right, now the way that I drew the height lines, now just so you know, the height lines aren't actually there, right? So if you go outside and you look around you, you don't see dotted lines all across the world that represents the height. Okay, and that's important to know because when we draw voltage or equipotential lines, we draw it in the same regard, and it basically represents the same thing that height represents for us. So let's fill in this idea and this concept of the gravitational field here. When we raise it up to a height, we know it falls, and when it falls, it starts to move. And so the way we could represent that statement right there, okay, we raise up the object, we can say the object has gravitational potential energy, which is equal to mgh. Okay, and we see that H come into play right there. When we raise it up a height and we release it, it turns into kinetic energy, okay, or the energy of motion, 1/2 mv squared. That idea right there is very important, Okay, when we have a change in height, we are giving the object that we are increasing the height of some amount of gravitational potential energy. Now, here's a very important concept here. Make sure you pause it and you write this down as well. Potential energy is stored within the field. Okay, and this is a big idea and a big concept in physics that you need to fully grasp and understand. A lot of people believe that energy is stored within the object itself, but that cannot be the case. Let me tell you why. Let's say you have once again, an apple, and that apple is just sitting on the floor. Okay, so if the apple has the potential energy stored within itself, it could release that energy in one way or another. Okay, because remember, energy cannot be created or destroyed. It just goes from one form to another form. So if this apple sitting on the floor, if the potential energy is stored within the apple, that must mean that the potential energy that's stored within the apple can turn into another form, and that other form for us is kinetic energy or motion, right? So if the apple all of a sudden just starts to move, that'd be really weird. Or let's say the apple all of a sudden starts to combust, right? So potential energy can turn into heat. And that will be really weird, okay? Spontaneous combustion. And so the idea that the object itself stores the potential energy is not a correct statement. But what we can say is that the potential energy is stored within the field, okay? Not within the object itself. All right, so with that out of the way, let's actually finish this analogy and go to potential, okay? Or voltage. So we're going to start off, we're not going to draw grass here, but let's start off by drawing a positively charged object. All right, so if we have a positively charged object, one of the very first things that we did is we learned how to draw field lines. And because it's a positively charged object, the field lines emanate up and away from the object. Now, the closer you are to this object, let's say right there, okay, you are experiencing a stronger field. The further away you are from the object, you are experiencing a weaker field. And we know that from the formula for electric field, which is E is equal to KQ over R squared, where Q is the magnitude of the charge and R is the radial distance away. So because E and R have an inverse relationship, the further away you are, the weaker the E field, the closer you are, the stronger the E field. Now, that's just like the gravitational field, right? The closer you are to the source of the gravitational field, the stronger the gravitational field will feel. The further away you are from the gravitational field, the weaker the gravitational field will feel. Okay, and much like the gravitational field, we also can discuss that a charge stored within the field can also experience a electric potential energy, and that was from the previous video. UE is equal to, let me check my notes, K Q1 Q2 over R, or the other version of QV. So if you remember, what this formula tells us is if we have two charges, one charge producing the field and one charge being a distance away from the field, and that distance away is represented as R, there is electric potential energy stored within the field. Now, keep in mind that I'm using the word potential energy here, which is different from potential or voltage in this case. All right, so let's actually discuss what is this voltage. We still haven't discussed what voltage is, right? We're just doing a lot of review leading up to this idea of voltage. Now, voltage is synonymous, or you could think of it like height. Okay, much like how we drew these dotted lines to represent the height lines, we can do the same using dotted lines for the electric field. Now, I'm going to focus on the middle field line here, just to show you how we can draw field lines. So field lines are drawn perpendicular to, the potential lines are drawn perpendicular to the field lines, like so. And each one of those can represent a different voltage. For example, here, this voltage can represent, because it's really close to the charge, let's say that one has, 100 volts. And the further away we are, the voltage can get weaker, so we can call that 1 volt. All right, and each of these marks in between can represent a different voltage. Now, the much like the height lines that we drew over here, okay, the height line for here is 1 meter. The height line for here is 1 meter, even though they're under two different field lines. Okay, 1 meter, 1 meter. Okay, all four of those perpendicular lines represents 1 meter, even though I have different field lines or gravitational field lines representing them. We can do the same over here. So if we take a look here, that can be 100 volts, and so can this. Okay, this right there can be 100 volts, and so can this. So everything along this equipotential represents 100 volts. And here can be the next voltage. Here can be the next voltage. Okay, I'm going to skip the other ones and just go straight to the top. Okay, remember, the equipotential lines are always drawn perpendicular to the field lines. So anything along here will represent 1 volt. Now, this is a very important idea, especially when it comes to how much work is being done on the charge, and we'll review that in a little bit. Okay, so as we see here, the field lines, they are always drawn radially out from the charge, and the equipotential lines are always perpendicular. Now, this is emanated from a single source. Now, what if we have multiple sources? In this case, what if we have an entire line? Now, let me make that a little bit straighter. An entire line of positive charge. Okay, if we have an entire line of positive charge, let's see, and these are my field lines there. Okay, instead of drawing out the field line like a almost like an onion looking thing, okay, where it's like arced, we just follow the same rules. The equipotential lines are always drawn perpendicular to the field. And so because here the field lines are just going vertically, okay, the equipotential lines will just be horizontal right there. So this could all represent the same voltage. Let's say positive 200 volts, and this all represents a voltage, and this all represents the same voltage. Okay, so the potential lines can either look like circles emanating out away from the charge, or it could just look like horizontal lines emanating out away from a line of charge. All right, now if we have two charges, okay, let's do a positive and a negative charge there. And if we were to draw a field line, okay, this is the classic model of field lines. So, okay, and I know there's some that go out this way, and there's some that go in this way, like so. What about the equipotential lines for here? Well, the rules are still the same. Okay, so we can say anything along here represents, let's just say 100 volts. Okay, and as we go out, okay, so that line, let's say that one represents 90 volts. Okay, oops. We can say this one represents 90, this one represents 90, that one represents 90, this one represents 90. So I'm just going to do a quick 90, 90, 90, 90. All right. So hopefully you're starting to get my drift here. And as we emanate out, this can represent, let's say this one is 20 volts. Oops. 20 volts, 20 volts, 20 volts, 20 volts, 20 volts. Okay. And if we go on the other side, we can say the closer to the negative one, just so you know, that's 90, that's 20. Let's actually finish this. There we go. It can get a little messy, but I think they're fun to draw. All right, there we go. All right, on the other side, let's actually do this in a different color, just so I can prove a point here. Let's make this red. Oops. All right, so this can be like negative 100 volts. This can be negative 100, 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 negative 100. All right, so I'm just gonna write that there. Write that there. Okay, and the further out we go, our magnitude gets smaller. So this can be like 70 or negative 70. Okay, so that's like negative 70 volts here. Just gonna write that nice and big. This is negative 70 volts. And let's see, let's get a little bit closer. Let's make this negative 10 volts. Right. There we go. All right, so this is like negative 10 volts. And the reason why I'm doing this is we can see, so let's say this is negative 10 volts and here this is 20 volts. Eventually, according to the number line, we're going to reach a point where right in between, there's going to be a 0 volt line. And let's do this in purple, just so I can prove a point right there. Here we have 0 volts. The cool thing here is, remember, one of the rules for drawing the equipotential lines is that they have to be perpendicular. And lo and behold, perpendicular, 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 perpendicular. We have the 0 volts, and it just goes straight down. Now, it won't always be this case, like the 0 volt line won't always be straight up vertical like this, but for the sake of our drawing, I made it so that it looks just like a 0. Now, you might be thinking, what does it mean to have negative voltage, right? So we're like, okay, Mr. Lee, you're telling me that voltage is like height, and it makes sense. So if I raise an apple above a height of 0, okay, it has a positive height, and if we reach the floor, we can say the height is 0, right? So that's kind of like here. We can travel, let's do yellow here, all right? So here we have a high voltage, so we have like a high height, and if we go from there and we go lower and lower and lower, okay, we go from a high voltage to a low voltage to a 0, okay, and where 0 voltage is like the floor. But what about this negative voltage? Well, the negative voltage, if we were to go back to our analogy up here, negative voltage is kind of like if we were to have a hole in the ground. Okay, and let's say this grass here is called 0 meters. Anything below that will represent just a negative height. So this could be negative 1 meters, this could be negative 2 meters, this could be negative 3 meters, and this could be negative 4 meters, right? And so if we are going from 0 volts in this case, and we can say we go from 0 volts to negative 10 volts. From negative 10 volts, we can go to negative 70, and then we approach negative 100 volts, right? So we can see how we can go from positive voltage to 0, and from 0 to a negative voltage. All right, so that's just the idea and the concepts behind exactly what is voltage. In the future videos, we're going to go a little bit more in depth with what we can do with this newfound knowledge. But before we get there, let's wrap up our notes. Okay, let's say, what do we have there? Formula. Can't believe we don't have the formula yet. All right, so the formula for voltage is equal to KQ divided by R, where Q is the charge, okay, and R is how far away you are. So if I'm here, I have a big R versus here, I have a smaller R. Okay, the bigger my R, here we go. So this is R big. Okay, if my R is really, really far away from the charge itself, Q, my voltage is going to be small. Okay, voltage is small. Here, my R is small. I'm really, really close to the charge. Therefore, my V is big. Right, I have a lot of potential. All right. Now, the only other thing that I can introduce to you is the calculus version of this formula. So let's make sure we have this highlighted. Very important. The calculus version of this is delta V, or a change in voltage, right? We discussed that a change in voltage is kind of like a change in height. So if you have a change in voltage, that means that we have a negative antiderivative E field times dr, okay, where r is also a vector. All right, now where the bounds are represented by r, and let's go exactly what this means. So if we have a change in voltage, that must mean that we are having a change in E field. So that kind of makes sense, right? So if we were to go back, actually that was kind of messy. Let's do, let's do this one. So if we have, let's see, let me just rewrite the formula there. V is equal to, or excuse me, if we have a change in voltage, you have a negative E dot dr. It is a dot product. So if you have a change in voltage, so let's say we are going from a high voltage up here, excuse me, a low voltage to a high voltage, we have a delta V. Okay, in order to do that, our E field strength changes. Okay, and it changes along a radial distance. Because if you remember, the closer you are to the charge, the stronger. There we go. The closer you are to the charge, so if your R is small, your E is big, right? And so here, if we go from point A to point B here, right? Because we're getting closer to the charge, our E field strength is changing along a radial distance. Therefore, we have a change in voltage, right? It all just ties up together nicely. All right, that was our idea behind voltage. There we go, or electric potential. One final note, Try not to confuse it with electric potential energy. That is something else entirely. But I'll see you next time. Bye bye.